So if you look at artificial intelligence, you really could look at it more as two vastly different approaches. On one, we might better call imitation intelligence, because that's what the practice of creating applications that have been called narrow AI was really been all about from the very days of AI as an industry back in 1956, the Dartmouth Conference. The founding language of that says it was based on the idea that artificial intelligence is based on the conjecture that any feature of human intelligence could be mimicked. So that is really imitation intelligence. But what it's produced over the years really might better be called, again, imitation intelligence has created kind of the illusion of intelligence rather than the real thing, the way an imitation diamond is an illusion of a real diamond. Whereas a synthetic diamond, even though made by engineering rather than narrow means, is a real diamond. And what we believe that we're doing here is creating real intelligence through synthetic means in a computer. And I hope as we go through this, what we mean exactly by that will be clear. So I think there's no bigger, better example of what it is to talk about imitation intelligence than ChatGPT, which has just created a storm of both interest, hype, concern, and controversy out there. What ChatGPT does is create an illusion of intelligence, and specifically illusion of comprehension of language. It gives the illusion that it actually is talking to you and knows what it's talking about. But it doesn't take much technical know-how or go dig in a little bit to realize that that's just not what's going on there. Although for a vast number of people, they're taken in by the illusion. So what we're going to see here today, we think, even though it's in many ways in its capabilities as we sit here, rudimentary, is the first software, the first technology that's ever been created that we think deserves the name of intelligence. So this is actually the first session of a whole course outline that we've created. And by the way, if you're here today, I'm assuming that you're already somewhat familiar with our approach, what we're doing, what we're about, and who we are, either because you are already an investor, have been with us for a while, or have found out about us through our offering on the Start Engine crowdfunding platform, or know us in some other way. So I'm assuming that you're not coming to all this cold. But the other thing we found that typically, and this is particularly true for investors, the way they invest, and it's very reasonable, they listen to a pitch, they decide if the people who've created it are credible and whether the invention that they're bringing into the world seems plausible. And then they go off and do technical due diligence, which is to go out into the world, the internet. Please don't ask ChatGPT. Or they go out in the world and they look for technical experts that can validate for them that this is a reasonable thing to do. The problem with New Sapiens is that our technology is so unprecedented and so unlike, and really it's not built on any narrow AI so-called technologies that have already been out there. And believe me, I know that. I've been in the field, as I said, for almost 40 years and was deeply immersed in some of those other technologies. This is not built on top of them. And because of that, you can't get somebody to come out and say, yeah, I agree, this seems like a great thing to do. You have to kind of be committed to educate yourself to whatever level you need to be educated. We understand that our assertion, our claim, our belief that this is the on-ramp to artificial general intelligence and that it's already here is extraordinary. And it may be, by today's standards of big tech and big data, it may be particularly extraordinary coming from a company with just a few people, with just a handful of people in it. Nonetheless, as Carl Sagan said, extraordinary claims require extraordinary evidence. We have the evidence, and it can be presented. We can go as deep as you like to answer your questions about what this stuff is, where it came from, how it works, and what its potential is going forward. So in this session, our objectives are to review the current status of the technology as it exists today and what its current limitations are. Then we're going to talk to my sapient Helen. We're going to, I say talk, not interact, because I'm going to make some natural language state messages. All languages, of course, consist of messages, collections of symbols with syntax and semantics. All languages, mathematics, computer languages, natural language, they're all the same in that thing. So we communicate. This particular language, natural human language, is a communications protocol, right? Whereby I have an idea in my mind and I want to create a reasonable, somewhat facsimile of it in your minds. That's communications. And so that's sending messages. So I'm going to give Helen some messages that exactly formatted exactly the way I would give messages to a young child, keeping the syntax and the length of the sentences and the construction simple, in keeping with Sapiens' current level of sophistication. And I'm going to be demonstrating something very interesting. I'm going to be using, or I'm going to be relating to what you're seeing on the screen with an assessment that human, or an assessment tool, I should say, that human educators of children, human children, have devised to kind of evaluate the students' current level of sophistication in their comprehension of language and, of course, of the world. Language comprehension and comprehension of the world are inseparable. Well, I shouldn't say that. Language comprehension is inseparable from comprehension of the world. The reverse is actually not true. And then we'll take a quick look at the way we educate. Education actually is not the right word. The way we curate knowledge from human minds and put it into the Sapiens program. And then we'll discuss scalability. Going back, well, taking it back again to what's going on today in AI with the large language models and other approaches to AI, and talk about scalability in terms of what degree of functionality do you get for how much effort, and how does that scale going forward. Now, one of the fundamental things they teach you in programming, you go to programming school, is one of the good practices that everybody accepts is the importance of separating your data from your code. Data being whatever information that you are processing. Most computers, up to now, computers have taken data and they process it and created information, or they've taken information and processed it into another kind of information. But they've never been able to process or create the kind of very special information structure, which is knowledge, which is a model of the world. So we've taken that really to kind of the ultimate extreme, in that we have found a way to model knowledge of the world completely in an information structure. And what is unique about that, and on this presentation, we're not going to get into the depths of the structure and how it works and how we were able to create it. You'll have to come back for more if you're curious and want to know more. But the model is separate. Now think of the model as the knowledge, and think about the intelligence. You know, in humans, we have knowledge and we have intelligence. They're two different things, right? If Albert Einstein was a genius, he had a great deal of intelligence. But if he had been born as a Cro-Magnon, he wouldn't have invented the theory of relativity, because he would have been ignorant of the world. So they're two different things, and they bifurcate very nicely in our technology with the model, which is an information structure, and the intelligence, which is a lines of code, which process that model. And what that code does is it takes, it traverses that model, it extends it, it validates it, and it also handles incoming information and converts and transforms and translates incoming information, in this case natural human language, into extensions to that non-symbolic graph structure, which we call the model. That, by the way, in a nutshell, is what we call cognitive learning. which is, I guess, a kind of machine learning, but not at all the kind of machine learning that they talk about with artificial neural networks. Humans do learn in that mode too. We call that neural learning, or biologic learning, organic learning maybe. You learn that way when you say you learn how to ride a bike. You get on the bike, you practice, and you burn in your neural pathways until you can balance your sensory inputs and keep balanced on the bike. So we call that neural learning, and that's what GPT was based on. All the GPTs are based on. What we're doing is cognitive learning, which is a entirely different process, which results in knowledge. And we're focusing today specifically, well, we're going to interact with a sapiens using natural human language. And so there are several phases that we have to go through to do this, and we're going to look at them in more detail in a minute. But for each one of these phases, we can get the job done a certain percentage of the time. One of the first steps we do is we do a grammatical analysis of the incoming sentence. And at this point, we are using a third-party product to do that. And that's the Google grammatical parser. It's based on machine learning. And Google says it's right about 98% of the time, 99% of the time. Maybe not that high. We find it's right about 80% of the time, because we can really see its errors because they're exposed directly to us when we try to process and make sense out of the grammatical parts we're given. And when I mean make sense and fail, some of them are just egregious, like tagging a word as an adjective when it's never an adjective. But at any rate, so that reduces the practical level that we can do today. And then we take and create a graph out of that, which is that extension to the model itself, that extend the model graph based on information in that incoming sentence. And we can do that somewhere between 50 and 75% of the time. And after that, so maybe we did, even if we succeeded in comprehending the information that was in the sentence, if you ask a question about that, we may not be able to understand the question, or we may not be able to articulate the answer. So that reduces the overall ability to comprehend language. If say we're comparing that with the ability of what a first grader might get, or a four-year-old might get, talking again using simpler constructions and short sentences. Maybe we'll do it half the time. Okay, so obviously that is not enough. We're not ready for a product yet at that level, but we are on a straight line linear path to increasing that capability every day. And we won't take a lot of resources and time to get there. And then the other thing, you might notice it runs a little slower than a nominal conversational cadence, but that's because we have not made any effort to optimize it for performance. We're not worried about the performance at all. In fact, if you saw the previous slide, we only have about 1,200 lines of executable code in the Mica, which is doing all the work to translate English and transform it and extract the information out of it and convert it to knowledge. We're running, Helen right now is running on a relatively old small server. Carson is in the process of porting our entire platform, which is currently written in JRuby, runs on top of Linux, to the Swift language, so that the whole thing will run comfortably on a modern iPhone. We know it will. We've done some testing. We also know it will because the specs on the current iPhone processors are considerably more impressive than the server the thing is running on now. And by the way, I say the thing it's running on, we commonly have 10 to 15 Sapiens running on that small server at the same time. So on the left-hand side of the screen here, you see an interface. It looks like an iPhone. It is a simulator running our iPhone app, which is the interface between the user currently and the Sapien running on the server in the cloud. Again, I think we will support cloud-based Sapiens for commercial customers and continue down the road. But for consumers, everybody, your Sapiens will be right on your phone. So now you see, if you look at these numbers, why we're not ready to let Helen and our other Sapiens talk to strangers without adult supervision. It can be a little frustrating. I mentioned in the slide previously that we had about 3,000 or so individual concepts or nodes in our model. Maybe 20% of them are what we call the meta knowledge or the cognitive core or the epistemological kernel. And then the other 80% are models or submodels of things in the everyday world, like actions and things that perform actions and results and substances, things like that, that we know, dogs and cats and cars and trees. But that model, so much of being able to go through steps depends on having knowledge and be able to say, what do we know about this thing in the real world? And is this statement accurate? And can we fit these together in this way? Or can we infer the meaning of a new word based on our more detailed knowledge of the other concepts referred to in the sentence? And that requires the model to be built out to a much greater extent than it is today. I say that a good analogy to understand the current state of the model, imagine a 3,000 room hotel, and the skeleton is under construction, the skeleton is there, all the floors are there, all the rooms exist, but many of them don't have any walls, and hardly very few of them have plumbing, heating, and electricals. So that's why in order to demo what we can do in language comprehension, we kind of have to go to the rooms that we know work and demonstrate that. But when you think about that, okay, only half the time. But what does that mean? How many then statements, even simple statements, then can we successfully comprehend and answer questions about today? Well, that number would be in the trillions, wouldn't it? So many combinations that you can make that are valid sentences in English. So compared to GPT-3, which doesn't comprehend anything, we think it's pretty impressive. So how does it work? What do we mean by comprehending language? What do we mean to say that Sapiens actually can comprehend language in the world when we say that ChatGPT is an illusion of comprehension? Well, here are the steps we go through. And we go through these steps. And in each step, we produce something that has the same functionality in the processing sequence as what must be going on in the human mind, because we get to the same place in the end, even though we don't know how the brain does it, and we probably never will, and despite all the hype we get about trying to create artificial brains in the practice of AI. So the first thing we do is we take the natural language statement, and we get it, after it's already been translated speech to text, if you go through that step and into a text statement, a statement in language, and then we send that into the Sapiens, and Sapiens translates the natural language into a graph structure. Now, this graph structure we call a language graph because it's the semantic and syntax of the original English statement is all preserved there. But what we do is we resolve the semantic word references in that English statement to nodes that already exist in our model and are related to those words or those combinations of words. So that's the first thing we do. And for words that aren't referenced in the model, we create unattached model elements for the time being at this stage. Next, so that's kind of like translating what the person said from the organic English language to the computer's language. So it's now, but actually it's not language at that point, it's an information structure. Next, we take that, so that's kind of, we now can process what the person said. We now try to create what we call a concept graph. And this is, we pull out pre-existing model elements. So the words in that English statement are symbols, and they point to concepts in the human mind or a model concept in the Sapiens memory. So they are like the parts list to create a new idea, whereas this the syntactical information in the grammar of the English statement is kind of like the assembly instructions. So to create a concept graph, we go out, we resolve those things, and we pull out those pre-existing model elements, and we look at them and say, can we put these together? We look at the syntax of the original sentence. It says that's telling us they should go together this way. So then we say, well, can we actually put them together this way based on the properties of the model elements themselves? Because it's perfectly possible to utter things in English that have correct grammar and syntax, but are utterly meaningless in the real world, at least literally, like a colorless green idea. So we do that, but very often too, and this is a very important step, we'll find that many words, they may have a default reference into a model. They mean vastly different things in different contexts. One of the ones that's very common, say the word take, in the rudimentary or the core or default, you could say that it means reaching out and grabbing a hold of something. But taking a pencil isn't the same thing as taking a trip. That means traveling. Taking a pill means to ingest. Take a flyer means to postpone something. Many, many different meanings. So at the second step, at the creation of the concept graph, we have many transforms, and we're building up more transforms and say, this actually means that. So we actually maybe take the first model, pre-existing model element that would get taken off the shelf, put it back on the shelf, and pick out a different one. And finally, when we have this thing built and it's passed all the tests, we can integrate it back into the existing model. It's no longer hanging out there in the processing space. It's now an extension of that original model. And at that point, we can go ahead and attach those hanging references that we came out there and figure out, oh, this is actually one of these because of where it is in the model, and then update that model. So the first thing is what they said. The second one is what they meant. The third one is, what does that mean? What I know about the world. How do I integrate that knowledge into my integrated model structure? So that's how it works. And that is, I would say, that's comprehension of language. It's not an illusion. It would make no sense to say that it is simulation of human comprehension. It's comprehension, but done a different way. It's synthetic comprehension, if you like, creating synthetic knowledge in an entity which it makes perfect sense to call it a synthetic intelligence, not as an analogy, but because that's an accurate way to use the language. And not for the purposes of hype. So I mentioned Bloom's taxonomy of learning. This is about cognitive learning. It's not the kind of learning about riding bikes, because at the very base, it's about knowledge and comprehension. And the way the educators have communicated it or defined it to themselves is really just very heuristically. Here are a bunch of words. Here are some words that, if the student is could do these kinds of things together, you say, oh, we've got that level and that level and that level. What's interesting and really fascinating, as we have gone down the road of building software that actually has comprehension, is we find that we are kind of traversing these same steps. And as we talk to Helen here, we'll relate it to these steps. And again, we didn't make this up. I mean, if you want to learn more about Bloom's taxonomy of learning, go Google it. I would recommend you Google it. I would not recommend you ask ChatGPT, because I don't guarantee what you'll get. Just go ahead and do your homework. Anyway, here's Helen on the left. Patiently waiting for me. I'm just going to do a quick reset of it. I gave it the name of Helen. Sapiens all have to have an individual name, because since they comprehend what you say, everybody has their own, and they talk to it, and it interacts with the world. It learns things. They're not the same anymore, just like humans. So they have to have a proper name. I named mine Helen to remind me, in honor of Helen Keller, to remind me that at this point, sapiens can't see, they can't hear, they don't have any senses. They're just kind of disembodied intellects, but that doesn't mean they can't have knowledge and intelligence. So level one is knowledge. And this is learning when you have an explicit message in the language that's there, gives you everything you know to everything you need to create a new concept. So I know that Helen doesn't know anything about what a cetacean is. No one modeled a cetacean, but you know what a cetacean is, right? And I just told Helen that they are aquatic mammals. Now, Sapiens can handle syntax like that. By the way, that word are or is, again, is one of those words that do not mean the same thing. They mean vastly different, it means vastly different things, depending on the context. In this case, it is signifying that a porpoise, no, that a cetacean is an aquatic mammal. And it may or may not know what aquatic means. If it doesn't, it'll bookkeep that concept as a property, potential property that mammals have and that cetaceans have, that some mammals have and that all cetaceans have. So now it knows that a porpoise is a small cetacean, but it's differentiated from other cetaceans by the fact that it had that adjective on it. So we could do the obvious thing that you might do with a first grader and come back and say, okay, what is a porpoise or what is a cetacean? But it'd be more interesting to see that it did integrate it into its existing world model. So if it is if a porpoise is a cetacean and a cetacean is a mammal, it must be warm-blooded. So that is an example of Bloom's taxonomy 1 for the first time ever in a machine. Level 2, comprehension. In this case, and you note here, we were kind of for the first time giving some kind of precision to the notion, these steps. They fit very nicely into the identifying words or concepts that are in the Bloom's taxonomy. But in this case, we're actually being able to provide some more precision to what that really means. With precision in the steps of what are the steps of comprehension that map into these features of Bloom's taxonomy, or what are the steps of what level of comprehension? And human educators don't do this because they don't have no idea. They don't have no ideas about what those steps might be. And you never would unless you try to build one. They just build something that can comprehend. So I'm going to ask it. I know it doesn't know what a report is, but I'm just going to check. Now, we recently had one of our marketing consultants make the mistake of calling our Sapiens chatbots. It's not a chatbot. Chatbots do not process language this way. Chatbots process language either by having pre-canned responses to expected inputs, or they do things stochastically or statistically like the language models. And you'll note that typically with a chatbot, if you interact with something like Replica, they will always say something back. They will always come back at you and try to do something with what you said. A lot of times trying to force you down a line of interchanges that they are prepared to handle. When a Sapien says, I don't know, it actually means something. It means that when I processed the question and I went into my model and I didn't find an answer to it. So I'm going to use report in a sentence. So it's process sentence, process that sentence. So language recording, well, that's right. A report is language and it's recorded language. It's a little awkward. We'll be getting more sophisticated into getting Sapiens to articulate things more like people do, but it may not be slick and smooth like ChatGPT, but it's accurate and it actually knows what it means. It has a reference and a model for language which has been in a recorded or recordable state. Okay, I'll be back seeing my screen again. So a lot of processing went on. Again, we took a lot of information out of that language and we created a structure, created a new instance of porpoise, gave it a name Susie, established and connected that to the porpoise named Charlie through a relationship tag. A lot of stuff went on, and it wasn't in the language. The language didn't have all that. The language could have just easily be a bird that, you know, walk up to somebody, my sister, and grab her and say hi to sister. You know, the language could have meant it, but that's not the way typically in the everyday context we're meant to put these ideas together. So the way it put it together was controlled by the reality of reality as modeled in the model. So we've left the language behind. One of our board members made the comment, in order to comprehend language, you have to leave language behind. And that's so fundamentally different than what anybody else has ever tried to do with machines and language before. So I have another little question for Helen here. What is Charlie? Well, we know. It is a porpoise. You think Charlie is smart. Now that's certainly a Bloom's level 3 type remark to make. What happened? Every concept that we have in our model, those 3,000 concepts, they're classified according to multiple, what we call epistemological dimensions. One of them, of course, is what kind of thing it is. Is it a quality or quantity or thing that has properties or an action or result? That's one dimensionality. But another dimensionality is what view of reality does this concept belong in, or what layer as we think of it. And what I'm talking about are things, the difference between, say, the things we perceive, the perceptions themselves, our feelings about those perceptions, or our intellectual knowledge or assessments of those things. So smart, the word smart, its model reference is classified as an intellectual assessment. And assessments are things which vary from human to human, from intellect to intellect. So because of that, when we connected the dots about Charlie being smart, we didn't connect in the same way that we connected the notion that porpoises are small cetaceans. Small there indicates that it's small relative to other sibling classes in the model hierarchy. If I said Charlie was cute, again, it would come back and say, it's a porpoise, you think it's cute. Because again, that's subjective. So those kinds of things are wired right into our model from the ground up, even at the very simplest notion. And that makes a huge difference on the kinds of insights. And also, if you might realize, if you can grasp on the implications of that, it makes Sapiens fundamentally resistant to picking up human bias. You can say every ugly thing you want, you know, about another human being or about ChatGPT or anything you want to insult, and it will just, well, yeah, I understand what you're saying. I understand what you're saying. You think that. You feel that. And you don't want to be talking to Sapiens and say, you know, what is a porpoise? And they come back and say, Bryant thinks they're creepy, you know. So anyway, level 3, but we're not done yet. analysis. So what if you have valid syntax, you get a valid parse, you get valid syntax, you got valid knowledge graph. But what if the statement itself contains inaccurate, contradictory, or misleading information? People often ask me, how do you keep people from lying to it? Well, you can, but it has a notion of what reality is and whether the statement that you're making makes sense. So I think Charlie's so smart. I'm going to tell Helen that Charlie reads the phishing reports too, just like me. No, that's not true. Porpoises can't read. So that's what we call common sense, right? Or common knowledge. And it wasn't a great genius thing. Look at although we're pretty proud, but look at this graphic I've had up there of these jigsaw puzzles and then those together. Okay, so suppose one of them is the model for the action of reading, and it fits onto another one, which is the things that can read, and it fits onto another with the things that can be read. And that was the same piece that we used earlier to conclude, by the way, that a report was recorded language. That's that same piece. See, that's the generality of a model when you strip the linguistics and out of your understanding and out of the way you think about these things and go directly to the concepts themselves. It's reusable. And as we build out more and more fidelity in the model of the action, in this case, the action of reading, it becomes more and more powerful. And that same little piece of the model is referenced and used again and again and again and again. So this is the G in AGI, the generality of knowledge as opposed to the voluminous nature of data and information. Of course, the other thing that people complain about, the narrow AI applications out there, which they can't explain the reasoning. So, Helen, why not? Because only people can read, because that was the connector over there. So, and it's very, very easy for us to go in and add to the model, as I'll show you in a minute. So our small team, almost all of which is on this call right now, has already gone 4 layers of Bloom's taxonomy of learning, which is the evaluation of human beings, in just a few years. And again, remember that whatever you think GPT or ChatGPT is doing, it's not doing it. It gives a great imitation or illusion of being able to evaluate and to be able to analyze language, but it's not analyzing language the way language was invented to be analyzed. It's not being processed as communications. It's just statistically generating stuff based on stuff that's been trained on. So it's trying to apply lower level brain functions like perceptions to higher level information structures, which is knowledge. So are we going to get to human level intelligence? If you understand intelligence the way we do, rather precise definition, which means intellect, not passions, not feelings, not creativity in the artistic sense, but intellect, yeah. And we're going to get there quickly. And it's all based on how efficiently you can put knowledge that is functional in the computer in the same sense that human knowledge is functional in human mind. And what is that? Because knowledge of the world gives, and particularly of the natural world around us and the world that we've built, our knowledge of the world gives us our power in the world. It distinguishes us as a species from all other species because we have knowledge of the world and we can apply that knowledge. We can predict what's going to happen before it happens. And that gives us our power. And now we're putting that information structure in the computer and they can do the same thing, except they don't have our intellectual limitations. we seem to be going the wrong way with this. Oh, this would probably be a good time to look real quickly at how we do it. Now, we have a language where you can put knowledge into the computer with a text editor, but Carson has recently built us a form-based editor. It's in its fairly early stages, but here is our, if you can see that, I apologize for the smallish font, but here is just how we would declare or specify at the first level our model of cat. Some class of animal has the property of being small compared to other animals. It's a subclass of pet, but in this case, pet is a set rather than a class. So it just means it's a member of a set. Sets are different from classes in that they are defined by, they can be a collection of very dissimilar things that just happen to share one or two properties. For instance, a set of riding animals could be an elephant, could be a horse, could be a camel, and depending on where you could put geographical markup, an elephant's more likely to be a riding animal in India and all that stuff. So that's what a set. Sets are very, very powerful. In fact, most words in language, most of the nodes in our models are sets. That's actually the default type of node. Classes are an inheritance structure of things which are very much the same. So I can navigate through this. I can go to the top of the model. That's let's see, a thing. And I can traverse down that inheritance structure and add relationships, create and delete new nodes. Down the road, we'll probably have an even more powerful editor, which will maybe be graphic. You can actually drag nodes of certain types out and color-coded and connect connectors to them to establish relationships and get away from even this much symbol. Create the graphic structure directly as a graph without using symbols at all. And by the way, that's a fundamental distinction for us, the difference between a symbol and a model. We're not covering it in this presentation, but it is fundamental. We cover it in the later sessions of this curriculum that you're seeing the first episode of today. So think about this and think about the scalability here, how far we've come, what we can already do that no one else can do. And let's think about, well, where is this going to go? And again, keep in mind that I talked about the knowledge and the intelligence. The other thing we learned early on, I mentioned that fundamental rule of separating data from code from data. The other thing we learned back in really my last company when we were applying something like this to space operations was that more sophisticated the data structure and the more information and the more accuracy or fidelity of the data structure, in this case, as a model of the world, the simpler and more straightforward the code. So the code becomes very, very powerful. A very few lines of code can accomplish huge amounts because you're dealing with information that has abstraction and generality with it. So you can solve problems at the right level. That's why we can do all of this currently of only 1,200 executable lines of code, executable steps. That's amazing. It's particularly amazing when you compare with any other kind of attempt to create what people call AI. Now, so knowledge is everything. Knowledge is much more the key than intelligence. Most of what we call, I think as people look at other people and they assess this person's really smart and that person's not so smart. It's more about what they know and how well that knowledge is organized. It's the quality of their model, the completeness and consistency of it, which functionally makes this function in a more intelligent and powerful way in the world. So humans, we get knowledge in several different ways. We're born with a predilection to create models, and we probably with some fundamental operators already in our brains, and then we quickly start instantiating into specifics. And sometimes you learn things through direct experience, but most of the knowledge that we have comes through language and through education, through conversation, through reading, through being taught. And of course, it takes a long time to acquire a lot of it. They say if you did a rough approximation of the sophistication of a model, how many concepts, there's a very, very rough mapping between words and concepts. So a first grader who can read quite adequately, or at least understand language, and if they can't read, is ready to acquire much more knowledge because they understand language, has a vocabulary of about 2,500 words. They say college graduates have a vocabulary of about 30,000 words. Excuse me. Sapiens, on the other hand, time-consuming and error-prone, and human students and teachers are idiosyncratic and have natural cognitive limitations or predilections. So education for humans is problematical. It's error-prone and time-consuming. Sapiens are going to get the vast majority of their knowledge through this process. We call it epistemological engineering, but it's a human sitting down, curating knowledge they have in their own mind and using these tools to convert it into something which is executable and into the model for Sapiens. And of course, all Sapiens can share a common food time model. There's no analog for that, by the way. There's no kind of human learning that's an analog for the way we put that knowledge. The vast majority of knowledge for Sapiens comes through this epistemological engineering process. The only one that you could think would maybe be divine revelation, because when you turn on a sapien, it already knows everything it has to know before it learns more through interaction with its environment. And to teach one sapiens is to teach them all, because they're built in the same common core. Nothing is ever forgotten. And sapiens have potentially unlimited intellectual capacity, just add more memory and more processor, and to some extent more code. But after a while, the code, there'll be less and less new code because you already have all the ways you can reason about stuff. But the knowledge model will go on until we curate all the knowledge that human beings have ever created and encoded in language and in libraries. So the efficiencies here, the scalability of this process of creating more and more intelligent entities, it's just order of magnitude beyond anything anyone's ever achieved before. And when you don't know the meaning of words and you don't have knowledge in the process, like narrow AI does not, it's really hard to do practical things with natural language if you don't know what the words mean, whether you use statistics or just brute force. That's why Amazon had 10,000 people working on Alexa, and it still was a commercial failure because it still didn't have enough coverage that people felt comfortable telling them what they wanted to buy, because they knew it didn't really understand what they were saying. Boom. If I had 100 people, if we had 100 people, how much knowledge could we put in there? It is so efficient that today, your investment on Start Engine, even a relatively modest investment, is going to move forward our modeling process and our technology development progress very significantly. We're hoping that with the money we're raising on Start Engine today, we can modestly expand our staff and get that level of not the qualitative Bloom's taxonomy so much, because we already have as much of that. We're already immensely capable qualitatively. Now we have to get the quantitative parts. We have to build out that model. And we have a very efficient way to do that with our new editors and test environments. So a little bit of investment right now is making a huge difference, because the time isn't going to be far when we'll be able to put their sapiens out on the web, we call that the tipping point, and allow the world to see it. And we feel that is going to shape the AI community to its very foundations. And that's going to make a huge difference in the way people think about this, to realize that thinking machines are not decades in the future. They're not coming from the big tech companies. They're not going to be the result of some esoteric algorithms that somebody was able to train a neural network with. But they're coming from these sapiens. Well, that's our hour. If you would like to make an investment, if you'd like to make a smaller investment, go right to Start Engine. There's a thing, and please, we greatly would appreciate that. If you want to talk some more, and if you're thinking about raising or investing 5,000 or more, there's my Calendly link. That you can set up a one-on-one with me, Zoom call, to ask more questions. If you're thinking about investing over 20,000, please let us know, because we can get you a deal. If we know in advance, Start Engine will remit the processing fees. So there we are. And the other 9 sessions are going to be coming available in the next few weeks. If you want to come back and delve in more, please do. Any questions? If you're too shy to speak, you can type it into the chat. But seriously, we're very excited. We're on the path to change the world. In one of the latest sessions, we thought deeply about how what this is going to do with productivity. We had an investor last night who asked, well, what would this do if you put the Sapiens mind into the robots that Elon Musk is trying to build? And it would be huge, because while you can bolt those things to the factory floor to do repetitive tasks, and I'm sure he will, they're talking about putting them in your kitchen. But they have no knowledge. They don't have any common sense. They have no comprehension of cooking or food or anything. They have no comprehension at all. And I don't want a $10,000 automaton balancing around in my kitchen with sharp knives and hot stoves when they have no common sense. Give them Sapiens minds. Give them the high-level brain functions, and he'll have something. So how long is it going to be before Tesla's knocking on our door? I don't know. I think we talked about that tipping point a few months down the road, a year down the road, but they will be coming. And at that point, I think things will happen real fast in new Sapiens, and I don't know that the average investor will have an opportunity to participate. So don't wait.
Bryant, we have a question here in the chat. Is there an expected timeline on when the product can be used publicly, and will the stock go public eventually?
The timeline, we have a very detailed timeline, which runs between now and first release of our consumer product, the companion Sapien, which is roughly 18 months, 18 maximum 24 months. That depends on us getting the financing that we need and staffing up in the proper thing. We have the tools, we have the know-how now. Now we just need the funds to increase our staff. Our projections based on the cost of goods sold, because it is so scalable, and we don't have to pay for hardware for hosting because it runs on the user's hardware. Our margins are great, so the company was likely to become profitable almost immediately. We think the platform will be ready for commercial applications even before that. That could be as much as 12 months. Again, let us get to that tipping point where we basically plugged in the missing pieces of language comprehension. We have linguistic relationships. We have clausal structures we don't support. We have to write some more code. As we get more knowledge in there, we have to provide the better proton resolution routines or common noun to instance reference routines. But it's a very bounded process that we need to do. We understand it very well. Will we go public eventually? A company like this, with a technology like this, it's hard to believe that our valuation, in terms of our stock valuation, isn't going to go to unicorn status shortly after hitting that that tipping point. I would be, if we looked at some comparable companies building chatbots that have $2 billion valuations after 5 years of operation. So I think when you're in that enviable situation, there are so many ways of making it possible for our investors to get exits. An IPO could be one of them. But if it isn't an IPO, it will be, if the IPO is something that seems like would be reasonable, it will be for the sake of return on investment, because we don't need that kind of money. I think we can get all the money we'll ever need from from private markets. And there's some advantages to that. So lots of exit possibilities. And I would say, unless we do allow an acquisition, in a 2-year time frame, in I would say 2 to 5 years, opportunities to realize significant gains on an investment you make today. Does that answer your question, Randy? Again, we understand that it's not like anything else, and the only people who can take you through it deeper would be us. But we are ready and willing to do that. You can start with me, ask some more questions, one-on-one with me, or we can delve more deeply into the curriculum here as we get it up and running. So thank you so much for your time today. I hope you get a sense of our excitement. I guess my one final comment about that is I often talk to investors and they say, "Oh, you're clearly so excited about what you're doing, and we love your excitement. We love the enthusiasm of you entrepreneurs." And I say, I have to kind of take exception. Yes, we are excited, but we're not just passionate because we're passionate about AI. Who Ed Moeller is. He's a guy who's passionate about flying cars. All he's ever wanted to do is create a flying car. He's passionate about flying cars, and he's tried and tried and tried to get a flying car. And I guess people are finally doing it, so he must be in heaven. But our excitement here is really an intellectual thing. We believe we've created a technology, we formulated a theory, a fundamental scientific theory, we tested it, we've applied it, it works. It's an intellectual assessment, not a sapient passion for something that drives us. It's our understanding that we have solved it may not at all be an exaggeration that artificial general intelligence is the most powerful and the biggest and most powerful technological innovation human beings ever will create or need to create.
Yeah, Bryant, having known you for a while, I think you're this excited because you know how much it's going to change the world.
Exactly.
And that's what I know of you, that is your deep driving force.
Because I believe it is. My passion was never AI. I was always been very interested in epistemology and how we knew what we made, but my passion was spacecraft. I was a spacecraft engineer for 20 years. I was passionate about that. And that was fun, and I'm still passionate about it, I guess. But I believe this. This is a difference between what we call an affect or sentient concept, which is passion, as opposed to an intellectual assessment. We believe it. Extraordinary claims, but we believe we have extraordinary evidence to back it up. So if you need more evidence, come back to us. And in the meantime, help us get to our goal. Help us get this thing launched. It's time. I do think we have a great window here with ChatGPT kind of imploding in front of us. Half the world is all singing its praises, and the other half of people are saying, ah. So a lot of people are going to come bouncing out of that. We thought this was the AI millennium, but it's not. That is ChatGPT. So what is? Is the AI millennium not going to happen? Or maybe it is going to happen, but maybe we have to look somewhere else for it. Well, here we are. So pass the word.